the end of the program. So the next talk is going to be by Emilio Trevisani from École Normale and the HES, who is going to talk about defects in CFTs.
Hi, thank you very much, and thanks for the opportunity to speak and for this nice conference. So I'm going to talk about some progresses on on understanding the kinematics of defects in CFTs with spinning operators. So this talk, disclaimer, will be very pragmatic. So it's the thing that I want to do is just to study what are the possible conformal tensor structures and conformal blocks that one can have in the case with defects. And so this is a work that it was done in collaboration with Marco Maineri and Edoardo Lauria. And okay, so let me start by try to motivate this work. So this work is about defects, and so here I wrote a list of defects, but of course the list is infinite, so these are just some of them. The first one is a trivial defect, so it's a case in which we consider a CFT and we don't consider any defect in it, but we can still consider what happens if we just study a submanifold, for example, a line in a three-dimensional space, and this can be treated by this formalism. Then there are actually more interesting ones like boundaries or interfaces, then line operators like Wilson lines, for example. There are monodromy defects, surface operators, and there are many also very exotic operators that one can define that are just non-local operator. So this is just a list of possible extended operators. So one of the motivation to study them is just because some of them are really relevant in physics. So I think if you want to study a theory with boundaries, well, that's quite of a physical question that you may ask. And so you may need this kind of tools. But another different approach is just to, it's a bootstrap approach. So this was also reviewed on Wednesday. So sometimes the idea of putting an extended operator, to probe extended operator can be useful actually to bootstrap the theory. And so in this sense, I want just to say that these operators, even if they are like, even the most exotic ones, are just in the end some states in your Hilbert space, in the Hilbert space of your CFT. So there's nothing very fancy about them. So if you want to actually couple them to the theory, you can do it, and you can see what if this is constraining. And so to try to motivate that in fact this approach is nice, let me, well, I'll put on this. So surprise, well, it's not a big surprise. Okay, a very slow surprise. And so here I want to okay, so it was a very bad surprise. Okay, thanks. So here I wanted to compare what happens in the usual CFT. So in the usual CFT, I will just consider Euclidean signature, and compare the setup with the defect and the setup without defects. So as we well know in a usual CFT, okay, one-point functions are zero beside the identity. then two-point function can be normalized to 1. Three-point functions are the first object proportional to some meaningful coefficient, the OP coefficient, and the first correlation function that depends on two cross ratios are four-point functions. And of course, one has the OPE of two bulk operators that can be used to constrain this four-point function by crossing. And so this is the typical crossing equation that we write in a usual CFT. And so now let me contrast this with the case of an extended defect. So for extended defect, I consider anything that breaks this symmetry to this SOP plus 1, comma 1 times SOQ, where P plus Q is equal to D. So P is actually the dimension of the defect, and so we can think that there's the conformal group acting on the defect, and then there are some rotation transfers to the defect. So just to be very, very clear, we can consider like a line in 3 dimensions, and we have a CFT on the line that lives on the line, and some rotation around the line. So everything is very simple, and in this setup, it's easy to see that already one-point function take a non-trivial expectation value, and if you consider one point in the bulk, so I consider points with hat are on the defect, while points without are in the bulk, and if I consider one point in the bulk and one on the defect, it's again written in terms of a new OPE coefficient, and then there are two-point functions of bulk operators. And these are the first functions of two cross ratios. And so there are two new OPEs that one can consider. One is the OPE of the defect operator itself. So if you consider, for example, a compact defect, for example, a sphere, you can do a radial quantization with respect to the center, and you can express that sphere in terms of just local operators of your theory. And so this is the kind of OPE that we would have. The other OPE possible is when we bring one operator close to the defect and we just expand it in terms of defect operator, so of states of the Hilbert space of the defect theory. So using this, a combination of actually these 3 OPEs, we can constrain this two-point function, that is the first non-trivial function, and we get this equation. And so what I wanted to just to claim is that well, this equation has some good feature. Of course, this is very well known. I'm just reviewing, but I want to review which are the good features and the bad features of this. So there is a clearly bad feature, and this is the reason why this equation was not really studied so much in higher dimensions. That is that it's lacking positivity. So one of the things that is really crucial to make the usual conformal bootstrap, for example, the numerical bootstrap work, is that, for example, if we take all equal external operators, the OP coefficient come as a square. And this is a very important feature that is used. Well, in this case, we have here a one-point function and here a three-point function that, I mean, they are not squares, and so even for a unitary CFT, you don't know the sign of this object. So it's a bit harder to make this program work. On the other hand, it has a good feature, that is that this crossing equation just involves 2 points. And well, this may be a bit trivial, but in fact, the kinematic of this bootstrap equation is much, much simpler. And so what I want to show in this talk is that so, for example, even for spinning operators, it has been quite a lot of work to understand how to make actual studies of Bootstrap even in this case of the 4-point function. But we will see that, in fact, as in a 2-point function, in the presence of a defect, everything simplifies quite a lot. And so, well, this, I mean, this is just to say that there are good features of this equation that we may take seriously. And then there's another point that I want to make, is that, in fact, lately there's been a great development in the study of this equation in 1 dimension. And so there are these new techniques that are analytic and that are based on the introduction of functionals that are very powerful, and maybe they will be very helpful to solve problems in 1D. And then, okay, if we can solve problems in 1D, we can think also that that 1D is a defect, and then we can couple it to a bulk and try to use this equation to constrain the bulk. So this can be also a point of view. And so for the goal of this talk will be just to show that, in fact, the kinematics of this is simple. And so to do so, I will do a very straightforward exercise that is just to define which are the conformal invariant tensor structures that one finds in this case. And I will also show how to do the same in this case, and compare a bit. And in the last part of the talk, I will also explain how we actually figured out some very concrete ways to compute these conformal blocks. So in particular, we find closed form for these defect blocks, while the bulk blocks, we find them in some expansion, in some cross ratios, which are still very nicely convergent. So in order to explain kinematics, one of the usual tools that we use in CFTs is the embedding formalism. So I want to show how to use this embedding formalism in the case of defects, where we introduce defects. So the usual embedding formalism is just the idea that since SOD plus 1, comma 1, the group doesn't act linearly on the points in RD, it's a nice idea to use an embedding space that is D plus 2 dimensional. So we have points now that have 2 extra dimensions. And okay, now on this space we have a linear action. And in particular, a good thing is that we have the flat metric of this RD plus 1, comma 1 that can be used to do just scalar products, and these scalar products are automatically invariants. And okay, the extra feature of this embedding space is that we can choose the points to be just null points. In fact, okay, we will need to get rid of 2 extra dimensions, and so one condition will be this one, and in the end we can do an extra projection on a special, so this defines a null cone, and then we can say that the physical space is defined by the null arrays. So we can just choose a section in the end to get back to RD. But this is not, I mean, this is all very well known. So what I want to say is that to apply this to the setup of defects, it's very, very easy. It's just the idea is to use a metric that is of an invariant under this action and the other one under that action. And in practice, the only difference is that now there are two different scalar products that you can build. And this metric will be the sum of the other two. Well, with this formalism, you can already see that one-point function, in fact, take an expectation value because it exists, in fact, a scalar product that you can write that is non-vanishing, and also that two-point functions are defined in terms of two cross ratios, which are defined in terms of this P1 dot P2 or P1 with the other product P2. So this is just for scalar operators, but of course you can you can use the same formalism for any operator with spin. And so I will just review very quickly what do we do with SOD tensors. So we consider them labeled by okay, Young tableau that is labeled by some integers, and so typically a tensor would have okay, many indices that one would need to symmetrize and anti-symmetrize in the correct way, and then also subtract the traces. A good trick is to contract them all with some polarization vectors, and the resulting object, so each line will be contracted with the same kind of polarization vector so that the symmetry is manifest. And so the resulting tensor is just a function of these polarization vectors. So you can also write it really putting the polarization vector into the squares as I like. And so the idea is that this tensor now is very nicely defined in terms of just some scaling rules. So in practice, the scaling in every Zi should be Li, well, of course. And instead, the mixed symmetry properties is encoded in this equation. So the fact that if you derive some, for example, Z2, and you contract it with Z1, the result should be 0. And this is just the fact that you anti-symmetrize on columns. And of course, the tracelessness is also encoded in this differential operator. A good trick is actually to use a polarization vector that squares to 0. And however, there's a problem then, that is the fact that if you use unconstrained polarization vector, you can just derive them with the usual derivatives. While if you use constrained one, you should actually change your definition of derivative. And well, usually we use some differential operator that actually we call Todorov operator, but one can actually use more generic differential operators that can, or if one wants, one can really just use projectors. So the idea is that one can derive all the Z, and then one gets some free indices. And these indices will not have the right properties of symmetrization, but one can use a projector into traces and, into some representation of SOD, and this projector will give you back the initial tensor that depends on the initial indices. Okay, this notation is a bit compact, but I hope it's understandable. I wanted to introduce this projector because it's actually quite handful in this topic, and in fact it will have some application in for the conformal blocks. And so the last interesting thing that we can do is to say that so we want this property of mixed symmetrization to be explicit. So the point is that every time we use so one object that is always 0 when we act with this operator is actually the antisymmetric combination of the first n z's polarization vector. And so these are actually very nice building blocks that we should keep in mind to construct tensor structures that are conformal invariant. Then I will explain how it works, the trick there. But now I want to say something about, so this was, first I said something about embedding for scalars, then SOD tensor, but what I want to say is that in fact the embedding is very nice because it gives to the operator in practice the same feature of an SOD plus 2 tensor written in that way, just with some kind of continuation. So the idea is that now an operator would depend on P and on some spins. We can again consider some indices of RD, but we can again embed these indices in the embedding space and contract them with polarization vector. So the result will be like a function of this kind, an operator contracted with this Zi. But the way to understand this, I think that is very useful, is to consider that the first line is contracted with P. It's like a tensor, but the first line is contracted with P, the second line is contracted with C1, and so on. And you can go on with all the polarization vectors. And then these, all these requirements are going to be, again, true. The only difference that you need to consider is that now the scaling in the first polarization vector, which is P, should be minus delta. So this is a kind of way that we treat operators with spin.
The length of the first line?
Yeah, minus delta. So this is a bit weird, but in fact, for all the purposes of this this formalism, you can just use this and it works. And in fact, in particular, one can one can use this same trick, and one will see that you can do the same. The only thing that you need to do is to add one box. So here, these boxes were like some Z1 up to Zn. But in fact, you should also add a box for P. And now, the claim is that these objects are the things, the basic building blocks that should be used to build conformal invariants. And so, just to give some examples that I think are fun, because I think also kids could have fun with them. So, if we want kids to join the Bootstrap community, it's important. So, so for example, if I want to study, let me use colors, a two-point function, of course, with operator in any representation, I can study how many of these, how many conformal invariant tensor structure will be there. We know the answer is 1. However, this is without defect. It's just usual conformal field theories. But the way to do it in this formalism is just to say that, okay, we have some, this operator will be labeled by some Young tableau, like for example, this one. And we consider that we pick this column of one operator and we attach it to the column of the other, and this one to this one, and this one to this one. And there's just one way to do it. So there is just one kind of tensor structure that we can write, that is the one in which we make two columns of the same size. So they will depend on some indices, and we just contract the indices one with the other, etc., like this. So these are going to be, this is a scalar, and respects all the properties of the mentioned before, and so this is a conformal invariant. So we can just count how many of these are there, and you see that there is just one for a two-point function. But you can use this trick also for a three-point function, and this is a bit more fun, I think. I think it's also worth to do just as an example, because let me consider the case of operator O1 and O2 that are traces and symmetric. So if they are traces and symmetric, it means that they have one row of some length minus delta, the second row of length L1, and the same for the second operator with some length L2 minus delta 2. So again, you can take these columns and attach them together, and you can attach them also to columns of this third operator. So you can ask, how long can it be, this column? And you see that the maximal length is 4, and then you can contract it with these two guys. And so when I write them like that, I mean that all the indices are contracted together. And you can classify all the possible things that you can have, and are not many. You have this, then you can have these. Or
Where did 4 come from?
because the length of this column is 2, so you cannot antisymmetrize 3 things. There's nothing else. And so you can have 2 from here and 2 from there, and so it's really just 2 plus 2. So this, I think it's fun, this, just because it's very simple. Of course, there are other ways to classify tensor structures. Also, another good feature is that, so this is written in embedding space, and it's useful to have structures written in embedding space, and it makes contacts with a lot of literature. And also, it can be very straightforward, generalized to the case of defects, as I will tell you in 1 second. But I wanted just to say one extra thing about this 3-point function. So there are just these possible tensor structure, and I wanted to tell you what they are. In fact, these are just products like pi.pj. So it's very trivial. Well, these ones are known in the literature. It's a paper by Slava et al., and these are called in that paper H, I, J. So this is I and J. And these are V, I, J, K, where this is I, this is J, this is K. And instead, these two structures were not defined in the literature, but they are there. And even if you want to study, for example, the OPE of 2 operators that are 2 vectors, and you want to say what is there, there will be an operator with okay, with the spin, so that is the kind 1, 1, 1. And this guy is there because there is this tensor structure. So let's say that this is a quite useful tool to have to count the structure like on a piece of paper. And the other thing is that we can very easily use this in the case of defects. Well, let me actually, I can use this same picture. So the idea is that in a case of defect, for example, I have a one-point function that we know that is non-trivial. How can you do this? Well, it's in fact, the idea is the same as this one. We can construct this with the same column. However, now we will use some metric GAB that is one of that I was defining before, but that preserves just one of the spaces. So this, for example, SOQ or SOP plus 1, comma 1. And so, so you can define, just contracting with this other metric, these objects are non-vanishing. And you can already see from here that you have already a prediction of which are the operators that takes a non-zero expectation value. Well, are the ones that have all the spins, SOD spin, Li, that are even. And this is because you need to use two columns to make one of these tensor structures. So this is it's a cute exercise when one can do it, and so we did it, and we had some counting of structures for some cases, and and for example, we could say that if you study a two-point function of two vector operators in the presence of defects, you can count 6 tensor structures. And also there are conformal blocks associated. So there is 6 of this kind and 6 of this kind. If you do the same in the case of a 4-point function without a defect, there are 43. And if you do same tricks for operators with spin 2, I mean, this number of structure grows very quickly. And so it's, I don't know, I think it's nice to have, to see that in the case with defect, we have numbers that are much more under control. And so we could, I mean, we could study many more examples. So these, for example, these conformal blocks are really trivial to obtain. Well, in the case of a 4-point function, the 4-vector conformal blocks are, I mean, a bit more complicated.
Is it accidental that you have the same number of structures in both channels?
No, it's there should be some group theoretic reason. Probably one can make it clear using reasoning like the paper by Patton on the counting of tensor structure. However, yeah, we saw that all the countings in all the channel match. Also for spin 2, you have, I don't know, more than 20, 24, and you also have 24 there and 24 there. So it's, and actually we went on for fun, but yes. So this is what I wanted to say about some tensor structures and kinematics. But the next thing that I want to tell is what we can say about conformal blocks, because in the end we want to have like the possibility to study this equation and see if it's doable, if it's better or worse. if there are good features for that. And so the status is like this. So I'll start to talk about this bulk channel. This bulk channel is the most problematic one, but one can understand why in some sense. The point is that the OPE here is actually the same OPE that is there in the 4-point function. So it's a bit simpler than the 4-point function conformal block, but it's not incredibly simpler. And so we couldn't find closed form expression for these conformal blocks, apart in some special cases. As in the 4-point function, it is well known in even dimension you have closed form expressions, but what we actually do in numerical bootstrap is to, for example, in 3D, we consider some series expansion in cross ratio. And the point is that then it's important to consider if there are some good cross ratios for which this series expansion converge more faster. And so these cross ratios were actually introduced by Slav and Matthijs, and are these row variables that were actually also mentioned by Volker. And so they just consist in putting the operators in a special configuration that is more symmetric. So you have operator O1, O2, O3, and O4. And you want O3 and O4 to live on a unit sphere, let's say, and while this one on a sphere of some radius r. So you can put here some, and they live at the opposite points. So this is a unit vector on that sphere, and here you have a different unit vector for this other sphere, for the point 04. And well, the cross ratios then are r, and some, and the angle between these two, n and n prime. One can prove that these are actually expansion of the conformal block in this cross ratios are are convergent exponentially, and so you can actually truncate it to and keep just a finite number of terms. And so this was a very important achievement for the numerical bootstrap. But so we wanted to do the same in the case where we have a defect, but well, this is actually quite trivial. So the point is that instead of the operator 3 and 4, now we don't have them anymore. We don't have anymore also the n prime, but we can put the defect here. So if we have a compact defect, let's say it enters the blackboard and it goes out. So it's a circle, for example. This still keeps the same kinematic configuration, and we can just use it like that. It's the same. The only difference is that this other angular variable will not be n dot n prime, but n, and again with this full dot and the same n. So it's that's it. And then the point is that now we can write these conformal blocks as an expansion in this in R. Sorry.
Essentially, why is it the same term? Shouldn't you like put direction of the defect?
But yes, what is, it's not defined by a unit vector defect.
Okay.
That is the point. So what we use is this projection onto the plane of the defect, if you want. So we project n there, and then we contract with itself. Then we consider some expansion of this kind and here there are some special function of eta. Usually this one, in the case of a 4-point functions, are just Gegenbauer polynomials, and in fact Gegenbauer polynomials can be obtained by contracting these projectors that I was defining before with some unit vectors. So these are Gegenbauer polynomials. This is equal to Cj of n dot n prime. In this case, we don't have n prime, but again, we have this metric. So what do? Well, we contract this with the metric. And you can prove, so these are contracted with the metric that projects onto the plane of the defect. And you can prove that, okay, these are new functions. These are some hypergeometric, so these are known, you can write them, but they are polynomials. So they, in the sense that if this is j, there is some minus j over 2 that truncates the degree of the hypergeometric, and so they depend on this variable n. So let's say that we find some nice kind of expansion, and now we want to fix which are these coefficients, and to do so there are a few techniques. One of the technique that we use is like it's this homologic of recurrence relation that it was defined in 2 dimensions, and there are ways to actually use it in higher dimensions, something of the same idea. So that the point is that conformal blocks that exchange an operator with some dimension delta have some poles in delta, and that happens when the Verma module associated to the exchange operator labeled by delta becomes reducible, and the residue at that pole are again new blocks labeled by these null states. And so this is a technology that it's actually what is used currently to compute conformal blocks for 4-point functions. And we saw that the same can be used to compute also these conformal blocks. So this would fix these coefficients. Then, of course, you can also just plug these in the Casimir equation and obtain a recurrence relation for these coefficients. There are, okay, many formulas that you can obtain, but let's say that there are, these are under control in the sense that one can really compute these to like any number, like any order. And so this, what I was discussing was mostly for scalar block, but of course the same can be said for spinning blocks. And just to mention, for spinning blocks, one of the tricks that it's used is to use some differential operator that, in some sense, give spin to the external operators. So these, it's nice because they actually, since the OPE is the same of a 4-point function, you just need to use the same differential operators. So you don't need to do anything. You open a book or a paper, you read them, you use them, and you can give spin to your bulk channel blocks. So most of the technology, in fact, can be recycled trivially. So in particular, so for this case, you can find blocks. So it's nice to write them like this. So there is this concept of seed blocks that doesn't have any tensor structure here in the 3-point function, and you can act with some differential operator and obtain a block for operators, external operators that have spin, and these will be associated with some special tensor structure in the 3-point function. So this you can just use the same form of differential operator. Everything is known. Instead, I want to comment about the defect channel conformal blocks. So those ones are, I think, are solved completely. So these are quite trivial. In fact, we can find them in a closed form. So the first thing that we do is to consider seed blocks. So again, these are conformal block that don't have any tensor structure in this Balto defect 2-point function, and it's easy to classify which are these one. You can and the idea is that this one you can compute them exactly, and the way to do it, it's fun. So the idea is that here you have an operator. Let me consider the case in which the two external operators, O1 and O2, are just traces and symmetric. So they depend on P1 and Z1, and this is P2 and Z2. So the idea is that these are just written in terms of some projectors, the same SOD projectors that I defined before. So this is an SO P+2 projector that is contracted with the P1 and Z1 on one side and P2 and Z2 on the other side, and then another projector on SOQ that is contracted with the same one, so P1, Z1, P2, and Z2. But I should tell you which operator is exchanged. So this operator is O hat. This O hat is it's an operator in the boundary theory. So it's labeled by an SOP plus 1, 1 representation that is minus delta. In this case, can be at most minus delta. Let me write with some hats since it's a defect. So this is SOP plus 1, 1, and then by the SOQ numbers that we write as 1 and as 2. And if the external operator are traces and symmetric, this is the most general case that you can have. And the interesting fact is that, if you want to exchange this operator, then you need this to have S1 and S2, but here you need minus delta and L. So you may wonder, so these were like projectors defined for like an integer number of boxes, but now we want to define it for a negative real number of boxes. It's a bit weird, but you can just do it. It's in fact very easy. So this is an analytic continuation that you can do that amounts to replace some Gegenbauer polynomial with an hypergeometric function. So it's very, very trivial. And yeah, the punchline here is that all the seed blocks are known, and then that there are some differential operators that you can define. These are very, very simple, and they act on the two legs and give spin, they give some tensor structures. And yes, and with these you can obtain, for example, very easily all the conformal block for any 2-point function for traces and symmetric operators, like. And you could do it also for more complicated representations, but well, it's not so useful. And there is one extra comment that I want to say is that, in fact, there are some good coordinates also for this defect case that are not these ones. And so if you want to write them in some series expansion that is exponentially convergent, you don't use those ones, but you use another one I'm not going to write them since, okay, these are actually known in a closed form, but the point that I want to make is that in those coordinates is fun because when you consider P even, then the conformal blocks reduce to something very easy that looks like R to some power, and then that is, well, in fact, delta, and then some, okay, irrational function of R. So they are really, really simple. And, well, this is another feature of this setup that is very promising because for analytic understanding of this two-point function with defect, the fact that one channel may be so simple, it's, I mean, it's really remarkable. For example, we can try to use some functional methods, or I don't know. We can try to use many of the analytic tools in this case, since this is so simple. So I hope that with this with this work, since now we have very explicit forms for the conformal blocks, for the tensor structure, there will be more work on this setup of a two-point function with defect. And yes, that's it. Thank you very much.
So until now, the Bootstrap studies of the defects, they focused on correlation functions of scalar operators, and usually the results were not particularly encouraging, like people had some difficulties getting. And so do you expect that now if you use spinning operators, things may change?
I'm not sure, but well, in fact, to be fair, there was also a study with boundaries and stress tensors. Only in the case with boundaries, that is a bit easier, the kinematic, even easier, because okay, this becomes SO1. But yes, I'm not sure, but yes, I think it's worth to think a bit more about this. I don't know, this equation looks so nice. Yeah, we may try to do a bit more. But yes, I'm not sure it will improve, in particular the numeric aspect. Maybe these analytic techniques, I hope they will enjoy something from this setup.
Good question. Okay, seems to be no other questions. Thanks, Emilio.
Thanks.